Good afternoon, everyone. I am Tony Robinson with MAPP, and welcome to today's webinar titled Smart Innovation, Bigger Returns, Cutting Hidden Costs in Injection Molding, presented by Bob Reese of MAPP partner RJG. Just a few notes before we get started. I will try to keep all attendees muted throughout the presentation, but please keep yourself muted as well to eliminate any background noise. We are recording the webinar, and it will be up on the webinar archives page in the next few days. You will need to remember login to access that page, so just reach out to us if you need any help with that. There is time for questions at the end of the presentation, so please use the chat feature to ask any of those questions. We'll get to them at the end. And if you have any logistical issues, you can use the chat as well, and I will help you troubleshoot. So with all of that being said, Bob, I will turn it over to you.
Well, thank you, Tony. I appreciate you, and I appreciate Matt giving us the opportunity to present this today. I'm pretty excited about this. So my name is Bob Reese. I'm a senior client solutions consultant for RJG. And what that means is I get the opportunity to go in and visit our customers and look at ways that RJG's technology can assist and help our customers be more profitable. I've been in the business 43 years. I've been in different aspects of the business, from started out actually as a process technician and worked my way up to a global process engineering manager for a large custom molder. So I want to share one of the things that I do on a regular basis is what we call a plant-wide assessment. And so we go into our customers' sites and we look at kind of the big picture of the process itself. And we kind of break that down financially. And that's what I want to share with you today, some of the tools that we use to do that, and even some of the results that we've seen. At the end of this, stick around to the end, because it's the best is saved for last. And we're going to do an ROI calculator to kind of show you what we have seen by implementing some of this technology. So excited to do that. So I'm just going to jump right in and get started, because we only have an hour and I tend to talk too much and get too technical. So I'm going to just move right into it. So the agenda, I want to talk a little bit about the molding problem. Then we'll talk about evaluating a process for risk. There's certain risk associated there. We see it all the time. We'll put a tool in a particular machine and it runs fantastic, and we'll move it to another machine and it doesn't run so well. And so by understanding the risk associated from the different perspectives of the process, it brings a lot of things to light. So we're going to go over that. I want to talk about production cost and their influence on profitability. What are the costs associated, and how do each one of those individually influence profitability of a process? Then I want to talk about measuring process improvements financially. It's one thing, it's wonderful when you can have wonderful PPKs, but the buck stops here, right? Money in the bank is what we're looking for. So I want to talk about measuring these improvements financially. This is going to be surprising to a lot of folks, but small process improvements in different areas collectively can net big returns. And I will explain that in a lot more detail as we move through the presentation. So that's the agenda. So the process, I mean, this is what we all do, right? We're in this business to make money. And to do that, we want to build a process that always produces an acceptable part, right? That's first and foremost. Build a good process. It has the ability to absorb normal variation. There's normal variation in this process. We see it every day. And so we need to build a process with that in mind. We know that variation's there and we need to absorb it. So things to consider. We want it to run at or below the sold cycle time. We want to run faster than what we quoted. But there's kind of a problem. Even though this process to, somebody that's new to the industry, it looks very simple. We close the mold, we squirt some plastic into this tool, and out pops a part and we sell it. Well, it's much more complex than that. Most folks on this call probably understand that. There are a lot of variables, and these variables can influence each other. So it's not just one single variable that we have to worry about. It's not even 4 or 5 variables that we have to worry about. It's the influence of these variables on each other. So I love this slide. It's kind of messy, and that's why I like it. It kind of is what the molding process, it represents the molding process well. The molding process has a lot of variables, and it can get very messy if we don't understand what variables we need to be looking at working on. So when we go in to do these assessments, these plant-wide assessments, we look at the entire process. And what I mean by that, we don't just go look at the settings on your molding machine. We look at the entire process, and we evaluate the materials that are being used, how those materials are being taken care of prior to molding. We look at the machine, we look at machine performance. And it's very surprising that, we see some late model machines that really nothing wrong with the machine itself. Somebody's changed a pump on a hydraulic machine or a servo valve or something like that, and it hasn't been calibrated correctly afterwards. That's a big thing that we run into. So just because it's nice and clean and it's only 3 years old doesn't necessarily mean that the machine performance is where it should be. So we look at every machine as we go through this process. We also look at the process itself, right? Which is the machine settings. Why did we question why are those settings like they are, and can we absorb variation with those settings? If the machine is performing correctly, and if the material is being well taken care of and conditioned as it should be, do we have a robust process that can absorb that variation? We look at mold performance. You can have the greatest material and the greatest machine and a good process, but if your mold is worn or not properly maintained or designed, even we can have issues there. So we will take a hard look at mold performance. Part design is not something that we necessarily, we do observe it and we do notate any part design issues that we see, but it's not, and make recommendations, but it's not something that we can necessarily change on the fly there. So I just wanted to show this slide to help understand that we're looking at the entire process. And I'll tell you, this entire process is what makes a successful process. If all these things are in line and they work as they should, they've been optimized as they should, you got great material, you've got a great machine, you've built a robust process, your mold is capable. These are the types of processes that you purge it out, you hit the green button, you start the cycle, and you make good parts for a long time. It's when one of these or two of these or three of these things are not right that it creates issues. And so again, that's why we look at all of these things. So I want to break this down a little bit further. So one of the methods that I use is what I call a process risk assessment. So as you can see, each one of these categories is here. We have material, mold machine fit, machine performance, and the process. Now, I haven't shown the whole sheet here. This is like a risk assessment. It has a risk priority number and some calculations that go on, but I just kind of want to explain it in its simple format here. So if we look at material, does it require drying? Well, if it's a hygroscopic material and it requires drying, there's associated risk with that. You got dryer performance. Do you have enough residence time in the dryer? So you could potentially see fluctuations in viscosity due to moisture in the material. So it automatically elevates its score if it requires drying because there is associated risk. Is the dryer in good operating condition? We'll take a look at that. It's got holes in the hoses or it's sized inappropriately, things like that are considerations. Are we using regrind? Regrind is wonderful. We love to see people using regrind. It's what our industry needs to use all of our scrap. But it does introduce additional risk in the material category. It definitely will create more variation in your material. Are additives incorporated on site? Are you blending colorants or anything like that on site? And if so, are they blended properly? Are you using the proper equipment and methodologies to blend it? Because if not, as you know, you could introduce variation lot to lot in your material. Are residence time requirements being met with dryer? And then the last one is look at pressure at transfer and fill time over the last 50 shots. And that gives us an idea of any effective viscosity changes that could be happening. So each one of these categories gets a risk, and they're cumulative, and those risks can add up. I'm not gonna spend a lot of time going through each one of these. I'm gonna read through them quickly. The mold or the cavity is balanced. What is the pressure at transfer? I'm gonna go over that in more detail later. Our hot runner temperature is balanced. Our hot runner settings within parameters for the material being run. All of those give us indications that things may not be right if they're not. The mold machine fit. So does the shock capacity fall within 20 to 80% of the shock capacity of the machine? Or are we using between 20 and 80% of the shock capacity? Clamp tonnage, are we using the appropriate clamp tonnage? Is there available first stage injection pressure? We don't want to be pressure limited when we fill this thing. Dropping down to machine performance, is the machine load sensitive? How much? I'll go over these in more detail a little bit later. Can the machine hold a consistent cushion? Is screw recovery consistent? Is hole pressure stable? And then for the process, we look at things like, is the process decoupled? Meaning, is velocity separated from fill and pack or pack and hold? Is process pressure limited? Is there sufficient hold time? Are profile speeds being used? If so, why? Are profile hold pressures being used? If so, why? Is there a documented setup sheet? Does the current process match the setup sheet? So you kind of get an idea what we're looking at. Now, let me explain this in a little more detail. In this situation, if you had a high risk material, you're drying it, you've got additives that you're putting in it on site, you're using regrind. So you've got a high risk material. I'm going to ask a question here and just think about this. If that's the case, what about your machine performance? What do you think your machine performance needs to be? Is good enough? Maybe not. It might need to be excellent. So that's the kind of the way that these things weigh each other. What if you've got high risk material? You've got an issue with mold machine fit. So you're using 10% of the shock capacity. So it could be residence time issues, could be other things. What about machine performance? Well, it probably needs to be very good. You're breaking rules. So I kind of want you to just get an idea of how we utilize this contextually. So this is our process risk assessment that we go through. And I'm going to break these down, right? I've kind of already done this, but each one of these can be really important and can really weigh on the next category. So been through the material, machine performance. When we talk about load sensitivity and things like that, let's take a quick look at a machine performance test. So this top left corner, this section, I don't know if can you guys see my mouse? You see that move, everybody?
Yes, we can.
Perfect, thank you. So injection speed linearity, this is simply a test of, this is the set speed of injection. This black line is what it should do, right? When I set it at 1.5 inches per second right there, the red line shows in our test what it actually did. So it almost did 1.5, it did like 1.25. But with this particular machine, we see that even though you can move the set point up to 2.5 inches or even 3.35 or whatever that is, when this machine gets to this speed setting of about 1.3.5 or 1.4, that's it. It has no more speed. So I go back to a comment I made earlier where a lot of times you run processes in a particular machine and it runs great, and because of capacity issues, you may move it to another machine and you may have all kinds of problems. Well, there's reasons for that. Let's say this is a hydraulic machine and this is a flow. This speed is a function of flow. That means if I want to go faster, I have to put more oil flow into the injection cylinder to go faster. The other thing that this machine must be able to do is compensate for changes in material. So it's called load compensation, which we'll see here in just a moment. But when we get, here's the story. When we get up past this point, there's no more additional flow to make adjustments for load compensation. So viscosity, when the viscosity does change with your high risk material, and it will, this machine cannot compensate. Basically what you're doing is running a 1969 Van Dorn, right? It's not closed loop. It can't compensate. It can't adjust for those the changes in effective viscosity. So this is one of the machine performance tests that we do, called injection speed linearity. This is the load sensitivity study, and it's a very simple test. What we're going to do is we're going to shoot plastic into the mold, and we're going to record how much pressure it takes to shoot that plastic in the mold and what the fill time is. And then we're going to make an air shot, and we're going to record the pressure that it takes to make an air shot and the fill time. And what we're looking at here is this load change. This load changed a lot. This gives us an opportunity to see, hey, when this material changes, easier to push or harder to push, and the load changes, which we can see by this pressure change right here, how much does the fill time change? That's what we don't want to change. We want to fill this mold in exactly the same amount of time. So we can see with this machine, we think that in most cases, 5% per 1,000 PSI of load change. So 5% fill time change per 1,000 PSI of load change is sufficient for most processes. This one is slightly over at 6.2. So that's a couple of the machine performance tests that we do. Here's an example of one that is good. I wanted to give you a good example. So we can see injection speed linearity there as a very good range of control for injection velocity. The load sensitivity is good. And this is another added test. It's just shot repeatability. We call it dynamic check ring repeatability. And basically we're shooting 10 fill only parts and we're weighing those shots. And we're looking for variation over those 10 shots. We just want to make sure that every shot gives us the same shot volume. All right, so that's machine performance. Another horrible example this is a real example that we seen not too long ago. This machine literally has 2 speeds. That's it. That's the controllable speeds that's available. Pretty hard to build a good process. Also, load compensation is horrible on this machine. It cannot compensate for changes in load at all. So mold performance, the next category is mold performance. Are cavities balanced? What's pressure transfer? And that's the one I want to focus on a little bit because there's a huge risk factor associated with that. So the pressure it transfers is basically related to how much pressure does it take to fill this mold, let's say 95% full. And if it's really high, like in this example, this is 18,000 PSI. In order for us to fill this mold mostly full, if we could put a pressure gauge right here, basically, we'd be reading 18,000 PSI. The reason that's important, the higher the pressure loss, dynamic pressure loss, the higher the risk. So this material variation that we talked about earlier, the higher this pressure loss is, the more effect the variation in your material is going to have on your part. Dimensionally, could be a short shot. It could be as bad as a short shot. So if this material gets thicker, if you will, harder to push, because of this high pressure loss, we're not going to be able to pack this part out nearly as well as we did previously when we didn't have a higher pressure loss. So the thing to take away from this is the higher the pressure loss during filling, and you can look at your molding machine and it's the pressure at transfer. The higher that pressure is, the more variation material variation is going to affect your part. Sorry. So in this case, 18,000 PSI is pretty high risk, right? I mean, anything around 14,000 PSI and less, in my experience, I'm not that worried about. It still can be problematic. But you get over 14,000 and then you get over 20, 21,000, 22,000, like some of these bigger thin wall parts, this gets really problematic. I have an example of that later in the presentation. So the process, we talked a little bit about this. Listen, here's the deal. You can have the best machine, the best mold, good material. And if you don't build a robust process, if you don't understand these variables and optimize these variables and build a great process, all bets are off. You're still not you're gonna have a less than optimum experience with with scrap. So looking at this again as a whole, we look at each category, material, mold, machine, and if we take this is a real example. So there's a pretty high risk here in material, pretty high risk. The mold itself, it has a high pressure loss. We've got a 3. 3 is the high risk. So I've got a high pressure loss there. So I've got material variation, I have a high pressure loss. We don't have enough clamp tonnage in this situation, right? So if you overpack, and the clamp tonnage is just right on the edge. If you overpack this part the least little bit, it's gonna flash. And when it flashes, you're digging plastic out of lifters and places you don't want to be. Machine performance is not bad. There's some speed control issues, but as far as the load sensitivity is not great. It's kind of a medium risk. There is some speed variation, some speed problems, like you can't control injection velocity well. So if you start stacking these things up, this is where problems come from. You got problems with material. You got a little bit of an issue with the mold. You got clamp tonnage that's, we talked about. Now we've got machine performance issues, and we've built a process that is not optimal. Now you start stacking these. This is the entire process dissected down to each category. This is how you need to look at these processes to be able to optimize. What do you optimize? What are your real problems? Hopefully that's helpful. So let's shift to factors that affect profitability. Let's talk about that for a minute. So material cost, obviously, that's one of the things that we're not making plastic parts without buying material. So material cost is a pretty significant factor in profitability. Therefore, I mean, we encourage everyone to use the least expensive material that you can get away with. Obviously, I mean that goes straight to your bottom line. The problem with that is low-cost materials generally have wider specifications on molecular weight. The additive content is not controlled as tightly. There's a trade-off. You pay less for it, and they spend less time making it, which is relative. So these things can cause viscosity shifts. These variations, and you're going to see it with the lower cost material. The way that can help our customers and clients is by using in-cavity process control strategies. And I'm going to explain a little bit how that works a little bit later. We can utilize, I've got this, what I've done for the last 6 years is go in and help our customers implement what we call decoupled 3 or cavity pressure control processes. And I have many, many stories I can share about the improvements that have been seen with really wide spec material. So the cost of direct labor, cost of labor in general, but the cost of direct labor is something that we can see easily. So it's a big factor. I know that probably everyone in this meeting has some pain point associated with the cost of direct labor. And if it's not the cost of direct labor, it's the cost of getting that labor, actually getting that labor at the machine. So obviously anything that we can do to reduce labor in any way is going to have a financial impact on the bottom line. So utilizing in-cavity pressure sensing technology, by doing that, we know the quality of the part. We can determine in real time dimensionals, or easy short shots, flash dimensionals, and in some cases, some cosmetic issues, not all. If it's black specks, we're probably not going to catch that. And most of the time we can do this without human inspection. We can tell you, our systems can tell you if they're set up correctly before the mold opens, whether you have a good or a bad part. Also, in-cavity process control minimizes process adjustments that are required. This is almost unbelievable, but I'm going to say it anyway. We just worked on a project about 6 months ago. Their their uptime for this particular job was about 70, between 70 and 75% floated around. Scrap rate, uh, close to 14%. But think about the uptime. So they wanted to run this. They could sell all the components that they could make, but they could only keep this thing running about 70% of the time. We put a D3 process in place, and this process ran the same process with no adjustments and very, very little production interruption for 6 weeks. 6 weeks, no process changes, and they were making on the average of 8 to 10 process changes a day, using really, really cheap materials, obviously. So it absolutely works if it's done correctly. Job efficiency, that's the uptime, right? Is really big. So utilizing in-cavity pressure process control eliminates under and overpacking situations that often cause parts to stick or robot removal issues. You see this a lot. So one of the big things for machines going down is the robot misses the part. Maybe the part stuck on a lifter. It overpacked in a certain area. It's stuck on a lifter. The robot could not pull it off the core, so it broke suction, alarmed the robot out, and the machine went down. And it took 15 minutes for somebody to get there to clear that, purge it out, restart it. And this happens time after time, day after day. And it has a huge influence on profitability. And one of the things that we can do is by controlling the pack in the cavity with cavity pressure, we're going to pack that part the same every single time, even if the viscosity changes. And it really can make some huge, huge differences in situations like this. Another one that I can think of is a cylindrical part that if you short it, it uses a stripper plate to push the part off the core. If you short it, it won't eject. So machine goes down, same situation. You got to wait for a technician to get over there. They're busy doing other things. They're setting molds. It takes them 15 to 20 minutes to get there. They finally get the part off the core. They restart it. Again, this happens 4, 5, 6 times a shift. It's huge, huge. Machines up and running at the required cycle is extremely important. So here's a story. This is some of our data. This is what we call our summary data. So this is historic data. This is a story that we see over and over and over. So stable production, you can see it. Each one of these represents a cycle. So you can see it's pretty stable. Everything's pretty stable. But we see here, we see an effective viscosity change. We're measuring the material viscosity, and we see that that material gets harder to push. The machine goes down, and it stays down for a period of time. This is our viscosity change here, as you can see. It stays down for a period of time, and then the technician shows up, and he plays with it he or she makes process adjustments for 20 or 30 minutes, and finally gets it up and running and back into stable production. And this repeats itself quite a bit. One thing I want to throw this slide in here because we do talk about this. So this is I believe this is published by MAPP, but it's kind of a cost median base rate for machines by size. So basically, what does it cost to run these machines on an hourly rate for maintenance, utilities, and things like that? So you'll see in our calculator that we're going to use this number, and I kind of wanted to show where it comes from. Scrap is pretty interesting. A lot of people focus on scrap, and to be quite honest, a lot of cases, scrap itself, like the dollar of scrap, isn't that significant. You're running 3% scrap, you're running polypropylene, it's $1 a pound, you got small parts. It's not that big a deal. Where it becomes a really big deal is when it gets to your customer. That's when things get super expensive, right? Obviously, it's good practice to eliminate scrap because then you eliminate the opportunity for those parts to get to your customers. That's really what we want to focus on. And by utilizing in-cavity pressure sensor for process control, we minimize the possibility of defects being produced. We can both control the process so we don't produce those parts, but if a part is made, a defective part is made, having those sensors in the tool, we can also look at the trace of that sensor for that cycle and make a determination is like, that does not fit the bill, and we need to reject that part, right? So we can, not only can we control, but we can also monitor and sort as required. So just a real quick kind of a show you the difference between a D2. D2 is just a conventional process that almost everyone runs. It's a velocity controls filling and a pressure control packing. So this shows a viscosity change. So what you see here, as this pressure goes up, these are overlaid cycles, multiple overlaid cycles. We have a post gate sensor at the highest pressure area of the part and an end of cavity sensor at the lowest pressure area. As you can see, this material gets harder and harder to push. Now the machine is not load sensitive. The fill time is staying constant as the viscosity changes. The fill time is not changing, but the pressure it takes to fill that part is changing. So the machine is doing what it's supposed to do. It's compensating for those changes in load. But if you look at the end of cavity sensor here, as this material viscosity goes up, it gets harder to push. This is how long it takes to get plastic to the end of the cavity. As you can see, it takes longer and longer. And this peak pressure represents how much plastic we actually put there, the pressure. And we get all the way to a point where we have a short shot. We've made a few short shots in here. By using in-cavity control, what we're using is this function right here, the post-gate sensor. We're using this peak pressure to tell the machine when to quit packing. So as you can see, we do the same viscosity change here with this D3 process, cavity pressure controlled, and very little variation in the cavity as compared to a D2. So that's how it works, or that's what it looks like when it works. I threw this in there because I used some of our old technology, the eDart, to show you that example. So I wanted to just kind of showcase our new platform, the Copilot here, and just a quick explanation of what this is. So here we're seeing real-time data. This is called a cycle graph. It is running a D3 process. So we're seeing our cavity pressure here. We have a template. So once we establish a good process, we push a button on the Copilot and it saves this dotted line for all variables. And that becomes our master process from the machine. So the red line is machine pressure. This purple line right here is stroke or volume or screw movement, if you will, screw displacement. And then we have cavity pressure here. So we save that template for everything. The summary data down here is our historical data, and you can see our limits. We set limits. This is how we would sort things. We're saying if the peak pressure at the end of cavity sensor gets above whatever the set point is or below whatever that set point is, we're going to reject that part. Now, there's a lot of other alarms that we can use as well. Then on the right side of the screen, there's just some simple operations. So here, there's a more complex graphic here, but on the other side, you saw some bar graphs and image of a machine with they turn green and red. It's more for, the untrained eye to look at and see exactly what's wrong. So just a usability change. So that is an example of the Copilot. There you go. You can see same stuff, peak pressure in the cavity, peak pressure in the cavity. The dotted line there is the template. Here, as long as the mold is matching the template, that is this template here, and as long as the machine is matching these two curves, you'll get green. So if you saw red here, you would know that something's wrong on the machine. All right, so that's a Copilot. So I get asked this question a lot. Can in-cavity process control improve any process? The answer is yes. It can. I've been doing this I've been doing cavity pressure control processing for at least 25 years, at least 25. And I can say that I've never seen a process, if it's done correctly, that didn't see some improvement. But like any investment, there must be a favorable return, right? I mean, is it worth, my boss always says, is the juice worth the squeeze, right? So this is where the ROI calculator comes into play. So I want to kind of look at that. See if I can. Uh, Quick confirmation there. Can everyone see my screen?
Yep.
Perfect. So I want you to think about this as this is not OEE per se. This is a job efficiency calculator. This is one job. So as an example, and the two of these are real data. Obviously can't share whose data it is, but it is real data. One of them I made up because I didn't have a high cavitation example on my computer. So the number of we're just going to go with an order, just to give us a baseline here. So the number of parts in this order is 36,000 pieces. The part weight, this is a big part. If you haven't figured this out, it's a trash can, 8.2 pounds. So I have some different examples that I want to share. One is a heavy part and then a lighter part, so you kind of get an idea. So it's a pretty heavy part. Uh, we got the runner weight, so there's no runner there. It's just like a cold sprue. We have total shot weight there. Have the cycle time, 52 seconds. This, that's not good. Okay. 52-second cycle time. This is again, true data. I'm not sure what's going on with Excel here. It's in and out. 52-second cycle. Okay, so going on down, it's only up 75% of the time. It's down a lot. And this is one of those situations that I told you about. It's using an air poppet and a stripper plate to eject this trash can off the core. And if it shorts a little bit, it sticks on the core. And so we've got to have somebody come over, cut it off, restart the process. Scrap rates running about 3.5%. That's what they told us. We saw something a little more, but hey, we'll go with their number. Cost of material per pound, this is HDPE and at 52 cents a pound. You may be getting it cheaper, you may not. This changes a lot, but this is the data that we have, 52 cents a pound. Labor rate, this is fully burdened labor rate. They're using a full-time operator, and this is at $27 an hour. That's fully burdened. That's everything associated with that labor. So they're using 100% one full operator. And so this is the hourly rate for this machine. It's a big machine. It's $60 an hour. And so if we get down to the bottom, we can look at total job cost. What does it cost to run 36,000 pieces? Well, that's the cost. That's what it costs per part to produce, right? Let's just throw a profit. Let's say that we get 10% profit off of this, right? So there's our selling price. And there's our profitability, our profit per part, right? So what I want to do, I want to just go through and show you some very small incremental improvements, right? And let's see what it costs. So cycle time, we got cycle time down to 50 seconds. We brought their uptime up to it was over 92%. I'm just going to go with 90% because it's a nice round number. We got their scrap less than 1%, but I'll just put 1% in there. Let's make it realistic. We got startup scrap and such. This is an instrumented tool. So we didn't change anything with material cost. We did change the labor rate. We went from, we figured out how to use a half an operator instead of a full operator. It wasn't that hard, but we did it. No change in machine cost. And so if we look at the cost to produce that part, it was $6.15. And it's, now it's $5.45. So what did we save there? Well, we saved, based on cycle time and uptime, 6.6 days. If you have capacity issues, you really need to start focusing and paying attention on details, because that just gave us 6.5 available days in this machine. Material cost savings, 2.5% or $3,837. And that's generally probably scrap. Labor cost savings was about 60% of this equation. And the machine cost savings, because of the days saved, was about 21%, 22%. So if we look at annual job savings on this, we're at $301,000. Now, let's talk about the investment. We talked about return on investment, right? They put 2 sensors in this tool, bought a Copilot, had to have the sensors installed. That costs money, right? Machine work. So, oh my. So, so I'm going to put the investment value in here. $28,000. And I know this sounds unbelievable, but if you're looking for fast return on investment and you know how to optimize and fix these processes, this is money in the bank right here. So ROI in days is 33, just slightly over a month for return on investment. And if we look at profitability, if you just want to look at this profitability number down here, based on this, we were at 10% margins, giving us, about, well, I have no idea what's going on with Excel. About 68 cents per part profit. We're now upwards of 20% profit, and our profit per part is $1.38. So that is an example. That is one example of a heavy part with a relatively long cycle time. I'd like to share another example. This is a medium-sized part. It's actually fairly large itself. It's 2-cavity. This is, that's the one I just did. Let's do the higher cavitation one. So here we have 1.4 million parts in this monthly production order. We have the weights here. We have the cycle time. We have the uptime. We have the scrap rate. Everything's the same. Cost of material. This is a nylon 6.6. At this time, it was $2.05 a pound, virgin material. The labor rate, $27 an hour. And that's kind of something that we just stuck in there based on the average that we've seen. It depends on where you're at. This labor rate, as you probably most of you well know, can go upwards of $35 an hour and even higher for fully burdened. So they were using 50% of an operator, so that one operator was running 2 machines. And then this is the machine cost. So if we go in here and take a look at what we did, so any good engineer can knock 2 seconds off of cycle time, right? And we did. We actually did. So it's amazing when you put sensors in a tool what you can really see. Where are you wasting time? So it's pretty easy to optimize cycle time a lot of times. We brought this up to 95%. This thing ran fantastic, man, and it ran a lot without any human interaction. We took the scrap rate less than 1%, but we'll put 1% in there to keep it realistic. We didn't change the material at all. We didn't change the labor rate at all. So it doesn't seem like per part. Now we're making a lot of parts, 1.4 million parts. A penny a piece difference doesn't seem like a lot. But when you start looking at things, 8% margins, we optimize that to 12.3%. And if you take a look at, I don't have, some of the things, there's 7.3 days saved on machine time, material cost savings, 1%, not huge. Labor cost savings, 23%, and then machine cost savings. So, it shows annual job savings, but we're only doing this on a monthly. That's 1 month. So it's about $12,000 a month saving on that, right? So that's a realistic view of a high cavitation tool. Takes about 3 months. I don't know what in the world is going on with Excel. Takes about 3 months to pay for that. I have another one here. It's more of the same. I'd like to, we have about 15 minutes left. I'm trying to get rid of this. I'd like to open it up to questions if there's any questions. I'd like to give people the opportunity to ask questions.
I haven't seen any questions come through in the chat yet, Bob. Maybe if somebody wants to unmute, they can definitely ask a question that way as well, or put it in the chat and I can read it out.
Okay, give everybody a minute here and see if there's any questions that come up. I mean, that's a lot to absorb pretty quick. And we certainly have the data to support everything, so.
Well, Bob, it seems like you did a great job explaining everything.
I suppose, one of the things that we didn't talk about here, and I probably should have, is material savings. Material's big, right? And I do want to just take a minute to talk about the opportunities, with materials. As a matter of fact, let me do this. Because we do have some time, let me just bring one of these up here and what if, here's a what if. I'll tell you what I'm going to do. I'm gonna make everything the same here. So I'm only going to optimize the material. We'll leave everything else the same. Make some realistic numbers here. Kind of want to just show the influence of, we'll even leave the scrap rate high.
Hey, Bob, can you hear me?
Sir? All right, so what if, I'll make sure everything else is the same. We're gonna use,
Hey, Bob,
cool.
can you hear me?
I can, yeah. Hey, Nick, how are you?
I lost.
So I'm going to make everything the same, and I think I've got everything the same. We're just going to look at material savings itself. Maybe. I'm really struggling with this Excel, to tell you. So let's say that we can buy a cheaper material. Let's say we can buy this material for 42 cents a pound. I don't know. Let's just take a look at that. What does that do for our profitability? It's massive, right? Material cost is definitely very influential. Even small savings in material costs or material. Let's make it 48 cents a pound. See what that looks like. That's still 5% increase in margins. Nick, I know you tried to ask a question. Can you hear me, Nick?
Bob, there is a question in the chat. How effective is D3 process if we only have a post-gate transducer?
Great question. And the answer is, I hate to say this, it depends, right? It depends on part configuration. There are certain situations where an end-of-cavity sensor is better. I've never seen a situation where a post-gate sensor, honestly, I have. I've seen one situation with a super thick part, very long flow length. And what was happening was the material in the post-gate area was freezing off before packing was done. So we couldn't influence that sensor with pack. That's the only time that I've seen a situation where a post-gate sensor did not make a big improvement as a control function. Thanks, Amber. Great question. Any other questions?
Hi, Bob.
Yes,
Bob.
Steve.
Maybe another part of that question is, though, that I think you're going to use end-of-fill for sorting of product.
Perhaps, yeah, I could. I could actually use both, right? It depends on what I'm looking for, and that's where, the question is, what are you looking to do? Like if it's a dimensional, if you're just looking to confirm dimensionals, sometimes both postgate and end-of-cavity can be very beneficial, right? If you know what those pressures kind of relate to how much material you packed into certain areas of the part. So if you've got a really high pressure at the postgate and a much lower pressure at the end of the fill, it basically tells you put less material at the end of the fill by this much as related to the postgate. So let's say you're looking at a warp issue and it's a compressive stress related warp issue, and you put a lot of material at the postgate area. So there's not a lot of room between the molecules for shrinkage, but at the end-of-cavity, you didn't pack it near as much, so those plastic molecules have a lot of room to shrink, right? And it can show you the different shrinkage in that part so you can see warp, for example. So the question is, what are you looking for? A lot of times end-of-cavity, if you're looking for short shots, end-of-cavity that's it, man. That's where you want to be, for sure. But the answer, Steve, is it depends. What are we looking for?
True.
Great question.
Right. Does anybody else have any other questions?
I'd like to pitch one thing, Tony, if I could.
Yeah.
So we do these we call them a gap assessment. It's a plant-wide assessment. And if anyone is interested in having us come out and look at your process holistically as a whole, as I've described it here, we'd be happy to do that. Please reach out and speak with someone with inside sales, and we can make that happen.
All right. Well, Bob, I definitely want to thank you for all the information you shared today. Like you said, it was quite a bit of information, and I definitely learned quite a bit today. Obviously, thank you to all of RJG as well for being such a long time and wonderful MAPP partner. Just a reminder to all of the attendees, the recording will be posted in the next couple of days along with the slide deck. If you can't access the webinar through our website, or you want the slide deck just a different way, you can also reach out to RJG, because they will also have obviously the slide deck, and they will have the recording as well. So feel free to reach out to them as well. And then thank you to all the attendees for being here, and I will now end the webinar. Everyone have a great day.
Thanks, everyone.
Oh, Bob. Oh,
Yes.
There is a question.
yeah.
Got a question. All right.
Last minute question. Would it be possible to get the Excel spreadsheet that you were using to demo the ROI calculations, Bob?
I think so. I think we're actually publishing a version of it on our website. But if there's somebody, yeah, if we could get contact information, I think we could certainly share that.
All right.
There was also a question, Bob, from Nick, trying to ask the question on the machine testing, how often it should be done.
Okay. Good question. So I personally, I mean, frequently, but I think annually, or when you suspect that there's a problem, right? So if you're doing it annually and everything's great, and then, suddenly something happens and you're not making good parts on a process that you used to make good parts on, it's a great idea to do machine performance testing, but at least annually.
Hey, Bob, can you hear me? It's Nick LaPree.
Hey, Nick. Yes, I can.
Oh, man, been fighting this speaker thing. That was one of my big questions, because you've been our facility. You see some of the stuff that we do. We have a lot of different people touching machines, which, calibration wise and whatnot. It affects that machine daily, depending on who messes with it. Everybody, not going to measure the same or calibrate the same. So as far as machine testing, doing some of the RJG stuff for a long period of time, we don't see that testing on machines as much, I guess, as should be. So that's one of the things that I had a question on of, like Amber said, I think yearly is good, maybe more often when we have things that change, calibration of pumps, stuff like that. That'd be
Yeah, for sure. Nick, you can also use that as a predictive tool, right? If you do this annually and you keep looking at results, even if you do it every year, and you see that your speed is good one year and it starts to fall off, the second year, and the third year is falling off even more, it can become a predictive tool, right?
Yep.
So,
I agree. All right. Thank you.
yeah, thank you.
Bob, you have a customer in Tennessee who actually uses the eDart as a pre-PM, and they monitor the machines, not just the injection unit. They also hook it up to the clamp, again, to look for pump, those kind of things. So it's a very good tool for it.
Yeah, that's awesome. Yeah.
All right. Thank you, everyone, once again, and I hope you all have a great day. Thanks.
Great. Thanks.